define mathematically what we mean for an algorithm to be private. Okay, and this is the purpose of differential privacy. So there are quite a few people in the room that apparently never really heard about differential privacy. So let me give you first the intuition behind it, right? So we're going to be looking at algorithms. So an algorithm is something that takes as input a bunch of data points and then produces an output, right? This output could be a bunch of statistics, or it could be a machine learning model trained on that data, whatever. And we're going to consider algorithms that are randomized. It's very important. It's going to be necessary, actually, for this property to hold. So this means that given some input, I have some distribution on a set of outputs, right? So even if you think about SGD is random, okay? So typically, if you run it 2 times, you might not get always exactly the same model. And so given an input data set D, there is kind of a certain distribution over the set of outputs, for example, the set of model parameters that the algorithm can. Okay? So an alternative way to see things is to think about the output of the algorithm as a random variable, right? That has a certain distribution. And then differential privacy essentially requires that if I apply the algorithm to one data set, here the blue one, or to another data set where I replace only one point, here the blue point, by another point, the red point, of course, the algorithm output distribution will change because I change the input. But what I want is that this distribution doesn't change too much. Oops. Okay, so informally, differential privacy requires that the distribution of outputs, when I change only one point and replace it by any other possible point, gives me similar distribution of outputs. Okay, so intuitively, if the distribution is close enough, it means I cannot tell by looking at the output whether a particular data point was in or not. Right? So I think it's intuitively right, makes sense. And so we have this notion of neighboring data sets, which encodes exactly this relation. So 2 data sets are neighbors if they are the same up to one point that was swapped. Okay. So how to measure this closeness is distribution? There are many different ways you can do that, and there are many variants of differential privacy that use, let's say, a different divergence. In the context of this talk, I will focus on the so-called rainy differential privacy, where we use a rainy divergence to measure this difference in distribution. Okay, so what this distribution, this definition says, it says that an algorithm A satisfies alpha, epsilon, rainy differential privacy for some parameters alpha and epsilon. If for all pairs of neighboring datasets, so all DD prime that differ in a single point, the divergence between these 2 distributions is small, bounded by epsilon. Okay, and so epsilon, of course, the smaller, the better the privacy guarantee. And alpha is more of a parameter. So if you change alpha, you change a little bit the notion of divergence. So we will get back to that later, but maybe it's not so important. And for people who know about rainy divergence, this is kind of the definition. But I will try to give a bit of intuition, but if you're not so familiar with divergences, this is not going to be so important, maybe the details of how we measure it, right? At least here, the important idea is we want to bound a certain notion of divergence between the distribution of outputs. For people who know about differential privacy, you probably have heard more about epsilon delta differential privacy, which is the more standard or original way of measuring. So it uses a different notion of divergence. But essentially, the good thing about this notion is that we can always convert whatever we have in this definition, we can convert in this epsilon delta definition. So they are equivalent in some way, but mathematically, it's often much more convenient to work with this version. But this is more of a detail. Again, if you don't know about epsilon delta DP, you can just take what I said. Okay. Why is it good? So, okay, definition. But of course, there are good reasons for the community to like this definition. The first reason, which is very important when you want to have privacy guarantees, is robustness to auxiliary knowledge. So this is encoding the fact that I want the privacy guarantee to make sense regardless of the prior knowledge that the attacker might have about the data. Okay, which is very important because in practice, you can never control how much the attacker will know. Maybe the attacker will have looked at the entire internet and find some additional information that will help reconstruct the data points, for instance. And so we want to be robust to this. And we can see this. So I'm going to try to show why this is the case. This is robust to auxiliary knowledge. So if you consider an adversary who tries to infer whether the dataset is D or G prime. So this is already a super powerful adversary, right? Who knows that the dataset is either this one or that one. So it already has like a very big prior knowledge. So it's a game, right? It's like the adversary tries to predict a bit to say, okay, the dataset was D or the dataset was D prime. It has some prior knowledge, maybe it thinks D is more likely or D prime is more likely. I'm going to denote that by P. And the information that it observes is the output of one execution of the algorithm, right? The algorithm is run, and then we are giving the output to the adversary. And now the adversary seeks to do a prediction. Notice that this is very similar to this membership inference attack, right? Because these two data sets are neighboring. So predicting whether it's D or D prime amounts to predicting whether it's X or X prime, right? And so now if we look at, let's say, the prior ratio, so this is how much, before seeing the output of the algorithm, how much the adversary thinks it is more likely that it was D prime compared to D. And then this is the posterior version where now I also observe X. Okay, and so I have a new knowledge, posterior knowledge as an adversary, which is updated based on the fact that I observed the output, which might give me information about whether it is more D or D prime. And then what we can show is that this notion of differential privacy essentially bounds a moment of this ratio. So this ratio of the posterior over prior. So what this means essentially in English, right? This is kind of saying that the adversary does not know how much more after observing the output of the algorithm, right? So it bounds in a certain way this ratio of how much confident I was before and how much I am confident now about whether it is D or D. Okay, and so this works whatever the prior knowledge of the adversary, which is the best we can hope for, right? So this captures the fact that maybe if the adversary knew a lot, even before seeing the output of the algorithm, we cannot do anything about it, right? We can just guarantee that hopefully the adversary doesn't know much more than before. And if the adversary knew nothing, well, then it knows nothing plus just a little bit, right? So this is really what differential privacy captures. It tells that by revealing the output of the algorithm, I will not increase the knowledge of the adversary by too much. Something very important also about this definition is that it is immune to post-processing. So what this means is that if I have an algorithm that is differentially private, then this holds also for whatever post-processing I do on top of the result of the algorithm, right? So this is very important because it means if my algorithm is differentially private, I can publish the result and then people can do whatever they want on top of that. It will preserve the privacy guarantee. Okay, so this is a very important property to have. And the last very important property that we want is composition. So this captures what happens if I run multiple algorithms on the same data and reveal the combined output of these algorithms, right? So in particular, in Rényi differential privacy, there is a very elegant composition property that is much simpler and much tighter than in this more traditional epsilon delta DP. So this is why people use this, is that if I have an algorithm A1 that satisfies alpha epsilon 1 RDP, and also an algorithm A2 that satisfies alpha epsilon 2 RDP, then the combined output of these two algorithms satisfy alpha epsilon 1% epsilon 2 RDP. Okay, so this captures the fact that if I do more computation and reveal more outputs of the same data, the privacy will worsen. This is unavoidable. I mean, if I keep revealing stuff computed on the same data, eventually I will not have privacy. But the point is that I can keep track of that with this composition, right? So if I do multiple computations on the same data, I can know how much privacy I have at the end by this composition result. Okay, so again, very important because in practice, for example, in machine learning, we're going to interact with the data more than once, right? If you think about gradient descent, you compute a gradient, so you need the data, but then you update your model, and then you now need to compute a new gradient in another location on the same data, and so on, and so you can handle this by composition. Okay. The last thing that I need to introduce about this notion of differential privacy is, of course, how to enforce it. So far, we have seen the definition. We have seen that it has good properties, but of course, it's useless if we don't have a way to enforce it or to make algorithms or computations differentially private. And it turns out there is a very simple way to do this. For any computation that takes as input a data set and returns a vector. Okay, so again, this F could be the thing that takes my input data set and runs a training algorithm on this data and returns the vector of the model parameters trained on that data. And to be able to apply this notion, there is this notion of sensitivity. So sensitivity measures how much whatever you're trying to compute can change if you change one data point in your data set. Okay, so it's kind of intuitively how sensitive whatever you're trying to compute is to a single data point. So typically you need to have a bound on that. And then what is called the Gaussian mechanism is something very simple. It takes F, computes the true computation that you want to do, so maybe train the model, and then add some Gaussian noise to the output. Okay. And then if you do that, so this Gaussian noise is calibrated based on the sensitivity, so how much this function can change if you change one output by another. And there is a parameter sigma, which tells you how much, right, the multiplicative factor of the noise. And then the bigger this multiplicative factor, the better the privacy, right? Remember, this is the epsilon, so the smaller, the better privacy. So if we add more noise, we get better privacy. That makes sense, right? All right, so this gives a very simple way to enforce this privacy definition. And notice also, that's very important, in differential privacy, privacy doesn't come for free, which you can see from here, right? There is what we call a privacy utility trade-off, because here, if I want more privacy, meaning bigger sigma, I'm going to be adding variance to the result, right? So I'm going to pay, in a way, privacy by having a larger uncertainty in the output. Notice that this is a centered noise, so, right, it's still an unbiased estimate of the true thing that I wanted to compute, and I know, of course, the variance of this estimate also, so I can do confidence intervals and so on, right? So if sigma is not too big, I can still work with this in most situations. But it doesn't come from free.
Also, if delta is not too big.
Of course, yeah. If delta is not too big, yes, as well. Yes. So if you compute things that can change drastically, if you just change one data point, then this will be a lost cause to try to make this private, which makes sense, right? Because I will need to add gigantic amount of noise to hide the contribution of a single point. But if you think about something like an average, then this is good, right? Averaging numbers in a bounded domain works well because a data point can change only by a factor of order 1 over n, the average, if I'm averaging n numbers. Okay. And thanks for the question. So I should have mentioned this at the beginning. I'm very happy to take questions during the talk. So please, if something is not clear, do interrupt. No question at this point. Great.
I have a question. I have a question in the properties of actually for immunity to post-processing. There's something maybe intuitively I don't understand. Because when I think about, for example, geo-indistinguishability, which is a differential privacy applied to geolocated data, you could imagine like post-processing that tries to denoise the GPS coordinates, right? So it's, to me, it's a bit weird to think about the fact that there is absolutely no post-processing that could like impact the guarantee, right?
Yeah, so it's the case. So of course, so long as this post-processing doesn't use the data again, and doesn't use the knowledge of the noise or the right. So of course, whenever, for example, if I use the Gaussian mechanism, I add the Gaussian noise. this Gaussian noise is kept secret, right? So this G is not allowed to, for example, remove the noise because it doesn't know the noise. But otherwise, it holds.
But it could use external knowledge, right? Or
external knowledge is fine.
Yeah, but external knowledge, for example, in the case of geolocated data, could be the history of past mobilities of that user.
Exactly.
So in order to get,
then this is related to this, right? If you use that, it means probably this attacker has a better prior knowledge.
Yeah.
So it knows already more. And so all this is saying is that we know that this adversary, whatever it knows to start with, it won't know much more. And this would whatever post-processing it applies. But again, this doesn't prevent an adversary that knows maybe a lot already to predict something. I mean, because then probably this attacker could predict even something even without having access to it.
Okay. Thanks.
All right. So maybe the last thing I want to talk about is what is called subsample Gaussian mechanism, which is the same thing as this, adding Gaussian noise, but before adding Gaussian noise, also, you execute this algorithm on a random fraction of the data set. So now my algorithm is I pick a fraction Q of my data set, and then I compute F on this subsample, and then add noise. Then we have this nice result that this amplifies privacy guarantees. So if I choose a small fraction of the data set, I get a boost of order Q squared in my privacy. Okay. So this is assuming that the data that was sampled remains a secret, right? It's not revealed. I reveal only the output, and I keep secret how much noise I add, the noise that I added, and I keep secret which portion of the data I used. Okay, and now the more I subsample, the better the privacy, which makes sense, right? Because it adds some uncertainty in a way, but we can precisely compute this. So this is the idea that random subsampling amplifies privacy gains. This is going to be very useful for stochastic gradient descent, for instance, where this is exactly what we do, right? At each step, we compute a gradient on the subsample of the data. Okay, and then very last part of the background, and then off we go back to decentralized algorithms, is how to apply this to machine learning very quickly in the centralized case. So let's assume for now that we have a trusted curator that has all the data, okay? So maybe there is some entity that everybody trusts, and all of us, we send the data to that entity. And this entity is in charge then to learn a model and publish a model in a way that is private. So to ensure that publishing a model will not allow whoever has access to the model to kind of infer too much things about the input data that was used to train the model. Okay, so in other words, we want to train a machine learning model with differential privacy guarantees. I'm going to focus here on kind of so-called empirical risk minimization formulations. So essentially, the idea is I have a set of model parameters, and I want to try to find the model parameters that minimize an average loss over my training data. Okay, so this is a standard formulation in machine learning. I have a loss function that measures how well the model with parameter theta does on predicting the label of point X, and I want to find the model that works best on average on my training. Okay. Typically, this loss is differentiable in the model parameters, so I can use gradient descent. So we're going to focus on that, and we can do a differentially private version of SGD. So probably most of the people here know already about normal SGD. So normal SGD would initialize the model parameters and then do a certain number of steps where you pick a random data point, and then you compute the gradient of the loss at this data point, and you update your model at the iteration t by essentially going in the opposite direction of that gradient. Okay, and doing this over multiple iterations until you converge or until you are happy. Right? So this is normal stochastic gradient descent. Now, the differentially private version is very simple. The only differences are highlighted in orange. The first difference is that you should make sure that the initialization doesn't depend on the data. And then the only other difference is that we just add Gaussian noise to the gradient before doing the update. Okay, so here you recognize the application of the Gaussian mechanism. The idea here is that we take the gradient. The gradient is the part that depends on the data. We have we can bound the sensitivity of gradients, how much a gradient can change if I change one data point. There are many ways to control that. You can make an assumption of the loss, on the loss, like Lipsitch, or you can use tricks like clip the norm of gradients empirically in the algorithm. And then you just add noise calibrated to the sensitivity and whatever sigma noise multiplier you want. Okay, so this is really a direct application of this Gaussian mechanism to SGD. And so to analyze the utility of this, typically for people who know how to analyze the convergence of SGD, this is essentially the same because there is already some noise in SGD due to the sampling. And here we just add a bit of additional noise due to privacy. So you can analyze this algorithm, the convergence of this algorithm in a similar way as normal SGD. And then for privacy, we can show that DP-SGD satisfies this alpha t over 2n squared sigma squared. This is directly just applying the subsample Gaussian mechanism, right? We add Gaussian noise and we subsample 1 point at each step. So Q is equal to 1 over n squared. This is why we have this n squared here, which we are happy about, right? Because this means the more data we have, the better privacy we have. And there is a factor T here, which is the number of iterations. This is because each time we do an iteration, we have to compute something of the data. And so we have to pay this composition, right? So it adds up. And so in the end, you get a factor T. Okay, and then if you want to have the best privacy utility trade-off, you should find the noise multiplier sigma and the value of T, the number of iterations, to satisfy the privacy guarantee that you want, while balancing the errors due to optimization and privacy. So if you do too few iterations, you will not optimize very well. But if you do too many iterations, you will add too much noise because of composition. So there is some kind of a balance to find. And if you do this, then we know results. I'm not going to spend too much time on this. We know what we can achieve. So we know, and these are kites. So we know essentially the cost of privacy for machine learning in this centralized setup. So this measures like how far the private model is from the true model without privacy. And we see it depends on the dimension, and it depends on the privacy guarantee, and it depends on n. Again, the more data we have, the smaller the cost of privacy. The details of this is not very important, but we understand quite well, at least in this central setting with a trusted curator, what is achievable, right? The cost of privacy in that setting.
And is it costly?
Well, as you can see from here, so if you have not so many data points and a very high dimensional model, then the cost is huge, right? Unless you do something a little bit more clever. So there are ways to leverage the structure of the model and so on. But in this worst case setup, you will be good when you have many data points and the model is not too high dimensional. Otherwise, this thing will become very big. Another way to see this is that you can always compensate the cost of privacy by collecting more data points. So maybe in setups where you have access to many data points, you can be fine because you can just use more data. But of course, there are settings where it's not so easy to have more data. And so then you should maybe restrict your attention to like simple enough models to get a good utility. Okay. So of course, here I assume I had a trusted curator. So this was not decentralized or federated at all, right? Because I assumed that there was this entity that everybody trusts that has access to the whole raw data.
So intuitively distributing the learning actually shouldn't be that good because if you apply DP
exactly.
small amounts of data,
so here you are
right?
you are killing my stuff, more or less. Exactly, right? So because we had this trusted curator, everything that happens during training was hidden. And we only cared about, we only needed to protect the final result of the algorithm, let's say the trained model, right? But now, this is good for utility, but not very realistic in practice. If I have many users, many parties that contribute sensitive data, it's not clear who this trusted curator will be, right? Maybe Google is trying to make people believe that they should be a trusted curator, then it's up to you and me to be happy with this or not. Personally, I'm not too happy about that. And as you get many people, it's hard to find a single entity that everybody will trust, right? So this becomes very unrealistic when data comes from different entities or different individuals, as in federated learning. So instead, what we can do is consider what's called local DP. So this is the idea that now I don't have a trusted curator. So each participant will need to apply locally differential privacy to whatever it sends to other people. Okay. So if you think again about this decentralized algorithm at the beginning, it means that all of the messages that are sent by a user should be protected by adding noise locally, instead of computing the final model and then adding noise at the end or something. Right? And so, like Sonia guessed, this will be bad, unfortunately, in terms of utility. The cost of privacy will become bigger because I need to protect more things now. Not only the final result, but also all intermediate quantities that are exchanged during the algorithm. Okay, and so we can see this from a very simple setup, which is the task of averaging n p-dimensional values. Okay, so very simple query. Everybody has a number and we want to compute the average. Then if we are in central DP, this is the error in square norm that we get under differential privacy. So there is dependence on how much privacy we want and on P and stuff, but the main important thing is that we have an n squared here. Whereas in this local DP setting, if everybody needs to protect from everybody else locally, then we lose like a 1/n factor here. So meaning the error in the estimated average will be a factor n larger in local DP than in central DP. And so this is very bad, right? Because typically this will work very well, even if I don't have so many data points, but this will become useless in most cases unless maybe I have millions of users. Right? Because otherwise this factor n is not enough to kind of kill the other terms that are due to privacy. And so this is exactly why we want to study other models. So this model is very, very pessimistic, local DP, because it assumes the adversary observes all the messages sent by everyone, right? Mm-hmm. And as I explained at the beginning, in decentralized algorithm, this is different because each participant only observes a subset of the message. And so this motivates the fact of maybe trying to study intermediate models between global central DP with a trusted curator and local DP, so that we can get better utility, but without relying on trusted partners. Okay, and so this is exactly what I'm going to do now, is introduce a variant of differential privacy that captures this aspect of decentralized algorithm. Okay, so it's going to be a relaxation of this local DP definition that we hope can give us better utility than what we have with local DP. So far, so good. Let me check the time. Okay. I should speed up a bit. Okay, so I'm going to introduce a little bit more formally decentralized algorithm now. So now we have all the background. Let's get back to decentralized algorithm. As I said, we're going to communicate over a graph, right? So the set of, I have n nodes, which are the users, and edges between them. Each user has a local data set. And a decentralized algorithm will rely only on communication along the edges of that graph, like I mentioned. Okay, so I'm keeping things abstract here for now about what the particular decentralized algorithm can be, but this is the setup. And like I said, the consequence of this is that each user V only has a limited view, observes only the messages it receives. And we want to use that, right, to provide better privacy guarantee under local DP, or conversely, better utility for the same privacy guarantee. So let's see how we can define this variant. So we call that network differential privacy. We're going to denote by OV the set of messages sent and received by party V. So this is the view of party V. This is the notion of neighborhood of data set that we consider here. We say that D is neighbor to D prime with respect to U. It means that all the data sets of all users are the same, except the data set of user U, which has been replaced by another. Okay, so. And then this is the definition. It's essentially very close to the normal RDP definition. The only difference is that we require that for all pairs of distinct users, U and V, and all neighboring data sets that differ only in the data set of user V, then the view of user V doesn't change too much, right? if I change the data set of user U. Okay, so if you take the view to be all the messages, then you recover local DP, because it means each user observes everything. But in practice, it's not the case, right? And so there is the idea that we only want to ensure this, like this divergence is small with respect to the view of each user V when we change the data of another user. Okay. So again, if you have a central complete graph, then everybody observes all the messages and you get back to it. Something natural is that we can have also a pairwise version of this. So it's natural in these setups to consider that maybe the privacy guarantees might be specific to each pair of nodes, right? So here I'm bounding for all pairs of users. I want to bound with the same privacy budget. But like we said, right, maybe based on where they are positioned in the graph, maybe some nodes will have better privacy, right? Maybe I learn less about a user that is very far in the graph. And so we can capture this by parameterizing the privacy guarantee by a function f that depends on the specific pair of nodes that we look at. Okay, and typically that will depend on the distance. We can hope that maybe f of uv is small if u and v are far away in the graph. I will skip this one. Okay, so this is now what we're going to consider. We're going to consider, or we want to prove this, right? So now we have relaxed the fact that there is someone that observes everything, and we want to quantify how much each user V learns about any other user, depending on the algorithm, decentralized algorithm that we use, and the graph topology that we have.
Sorry.
Yeah.
I just have a question about the assumption you made about the fact that user you only knows where messages that only sees the messages that comes.
Yeah.
It's rather a strong assumption.
Why is that?
The fact that he only knows that the messages that he receives, so he doesn't know where it will go next.
Yes.
So we're a little bit relaxing the.
Yes. So maybe I should make clear also that typically this graph is public, though. So everybody knows the graph topology. This is not secret, like who is connected to who. But during the execution of the algorithm, the assumption is that a given node only observes the messages that are sent to him.
He cannot see the messages that.
For example,
he will.
Exactly, V won't see the messages that these two nodes exchange, which I think makes sense, right? If you think about using secure communication channels, then this is the case.
Unless you have colluders.
Exactly. So we have also some results on collusion. So of course, it could be the case that maybe these two guys know each other and they exchange information, so they collude.
Mm-hmm.
We can also quantify this, but maybe for simplicity here, let's assume that there is no collusion.
Mm-hmm.
Yeah.
So very naive question. What are the messages that they exchange?
Sorry, yeah, this is gonna become more clear now. So
okay.
For now, this has remained quite abstract. I'm sorry. So this is exactly now going into looking at specific algorithms. So thanks for the question. And sorry for remaining a bit abstract. All right. So now we're going to look at a specific algorithm and show some guarantee. The algorithm is going to be very simple. So we're going to look at the standard objective in federated machine learning, which is each node V has a local objective function that depends on its data, and we want to find a model that minimizes the average of the local objectives of the participants. Okay, so that is quite standard. And what we're going to consider now is a decentralized SGD algorithm. So SGD in a decentralized manner, where the model is updated sequentially by following a random walk on the graph. So it looks like this. We're going to focus on the complete graph in this case. So all nodes are connected to all other nodes, but the algorithm goes like this. I initialize the model and give it to one user. The user does a gradient step with respect to its data and adds some Gaussian noise, as in the centralized version, and now sends the model to a random other user. Okay, so here we are exchanging model parameters. And it goes like this, right? At the beginning, this guy has a model, updates it, sends it to this guy, then this guy updates it, maybe sends it to that guy, and so on. Right? And so the intuition here is that maybe when this guy receives the model, of course, it knows that this guy has sent the model to him, but it doesn't know what happened before, right? Maybe the model here previously was here, or don't know, right? And so this is what we're going to exploit. The fact that there is a aggregation of updates, and the fact that the path that the model is taking is secret to the nodes. The nodes only know, let's say, the last node that they have received the model from. And so the gain in privacy will come from that. So this is the result a little bit informally for kind of simplicity. Here there are some assumptions on the objective function. So this is restricted to the convex case. And then what we show essentially is that if you choose the noise that you add to each gradient, that the users add to each gradient to be such that this algorithm satisfies alpha epsilon local RDP, so the local version, then this same algorithm satisfies alpha log n over n epsilon in this network DP setting. Okay, so what this is saying is that by relaxing the definition and accounting for the fact that each user only has a limited view, we essentially boost the privacy by a factor almost 1 over n, which is nearly optimal because in the central curator setting, this would be the same up to this log term. Okay, so this factor is up to the log term is optimal. We cannot hope to do better because, right, there is the limit, which is the trusted curator would be the best that we can hope for in terms of utility trade. Okay, and so it's quite nice because we cover exactly the privacy utility trade-off of DPSGD under central DP up to this log factor. There are some technical conditions, so notice that we need to do a quadratic number of steps here for this result to hold, which might be a lot. Maybe in practice you don't want to do that many steps, but this is only a simplification to have like a simple formula. Otherwise, we still have amplification if you do less steps, and we can compute that numerically. We have simulations in the paper. Utility analysis is the same as DPSGD because the algorithm does exactly the same as a central. DPSGD. The graph is complete, right? So each time you take a batch, which is essentially chosen uniformly at random. So, and the privacy, like I said, it leverages this idea of privacy amplification by iteration. The fact that when I receive a model, if the data of one user was used a long time ago, then I don't learn too much about the data set of that user. And also the fact that we have the randomness of the work that is secret, right? The nodes don't know, in fact, where the model went through before getting to them.
Aurélien, just a question to understand. So intuitively, it means that the more your model circulates in the network, right, the better the privacy, right?
Yes.
Somehow. It's a bit counterintuitive.
So, yes.
The better it is for the original sender, right?
The better it is for everybody, actually. So maybe what's hidden a little bit here is that each time you contribute, you do a new contribution, right? So this comparison is compared to each node doing rather roughly like n contributions in the central model. So you're using n times the data of each user in expectation in this case. Which is exactly what you do in the central setting also, like the centralized SGD, DPSGD. Typically, this result also assumes that you do n squared.
But you reach somehow the privacy of central DP after almost n square hops, right?
Yes, the idea is that you have to cancel the fact that. So if I do only one, for example, if I do only one contribution, maybe let's say I send my model to you, then I don't do better than local DP because the only contribution that I do, you see directly.
Exactly.
Okay, and so the idea is that you have to do sufficiently many such that you have, of course, you have composition that hurts you a little bit, but at the same time I'm spreading things. So then if I do T contributions, it becomes really unlikely that I give them all to you.
Mhm.
And therefore, I get this gain compared to local DP, where you would observe all my contributions.
Mm.
So this is why we need to do sufficient many contributions. Otherwise, you cannot avoid the worst cases in a way, right?
But in practice, you don't know somehow when the adversary, will be acting, right? Or when I mean, throughout the trip of your model in the network, right?
Yeah. So here this holds simultaneously for all nodes. So
okay.
The adversary against me, in a way, are everyone,
Mm-hmm.
and I can guarantee that no one will learn more than this, right?
Okay.
And again, though there are worst cases, there are cases, it could happen that I actually send all my updates to you, I'm bad luck, but this happens with such a small probability that you can swallow it in the, yes. And so this is exactly the reason why we need to do sufficiently many rounds, because otherwise it remains likely enough that maybe I can send 2 contributions to the same person.
Mm.
But if I do more, then it becomes essentially
The randomness.
very small compared to the rest.
Okay.
Thanks for the question. So this is a little bit what happens empirically. We verified that this works quite well. So this is showing the number of iterations of SGD and the objective function. So you want this to decrease. The red one is centralized DP. So if I have a trusted curator, right, which is unrealistic, but is in a way we were trying to get as close as possible to that. Blue is local DP, and so you see that, okay, it does quite poorly. This is the test accuracy. So of training objective and test accuracy, we see that local DP doesn't work very well. There is quite a large cost in the utility of the model that we get. But then if we look at the same algorithm under network differential privacy, we see that we get very close to the central case. Okay, so it's consistent with our theory. So I think I'm getting essentially to the end of the time that I had. I also took questions during the talk, so it's a little bit, maybe Karim, let me know whether I can.
You have 10 minutes.
Okay, I can use 10 more minutes. Great. Then I can tell you a bit about gossip, which I think is quite
Maybe you have a question.
Oh, sorry, yeah.
You suppose that you have one token moving, you only send one token.
Yes, yes.
Have you tried like parallel sending?
Yeah, exactly. So this is amazing because you're always anticipating to what I'm going to say next. So, this is exactly the last part is on algorithms where there is more parallelism, right? And nodes exchange kind of in parallel to their neighbors, right? So this is a limitation of the algorithm that I presented. It has this nice amplification of privacy, but it is very sequential. So, I mean, a good motivation for doing decentralized computation is also to do parallel computation. And unfortunately, in the previous algorithm, there is no parallelization at all, right? Because it's purely sequential, the model only moves. So one way to extend this is to consider multiple models that would do random walk. And as a matter of fact, this is something that we are also looking at. But here, I'm going to more focus on maybe decentralized algorithms that are quite popular in practice, which are based on the idea of gossip. Okay, in particular, they build upon the idea of gossip averaging, which is a decentralized algorithm to compute an average of numbers. And I'm going to briefly introduce this. So these kind of algorithms, they build on a gossip matrix. Essentially, it's a matrix n by n that is symmetric, non-negative entry, columns and rows sum to 1. And if I don't have an edge, or if I have 0, or if I have a non-zero entry in the VW entry of this matrix, it means that the nodes are connected. Okay, so essentially this matrix, maybe at a high level, you can think of as giving the weight that a user V gives to the contribution of another user W. And if they are not connected, then this weight should be 0 because it cannot aggregate its messages because they are not connected. Okay, and then gossip averaging, which dates back to, so there's this paper of Boyd, but they were already worked before that, works like this, very simple. Each node have an input value that they initialize and put it in an iterate. And then at each step, all nodes in parallel will essentially retrieve the current value of their neighbors and do a weighted average of the value of their neighbors according to this matrix level. Recall that this thing sums to 1 in columns and rows, so I am really doing like a convex combination of my neighbors. Okay, so very simple. I have a value at the beginning, and then I tell my neighbors, give me your current value. I do a weighted combination of their value and mine. Everybody does that, and we repeat this process for a few time steps, right? So this is gossip averaging. So this is only for averaging numbers. The cool thing is that we can build on this idea to do optimization, so to do a decentralized SGD algorithm, which is going to be quite simple. Again, we're just going to consider the same objective function of each node has a local objective, and maybe each local objective is the average of the loss over the local data points. And the gossip decentralized SGD looks like this. We initialize to some model parameters at each node, and then at each step, each node does a local gradient step, exactly as before in the random walk case, except that this, now all the nodes do it in parallel. And then they run a certain number of steps of gossip averaging on their current model parameters. Right, so at each step, I update the local version of my model using a gradient based on my data. And then I do a bit of steps of averaging with my neighbors. And then I take another gradient and so on. Okay. Of course, you can do only one step if you want, or you can do multiple steps of gossip averaging. Okay, so it's very simple. It's intuitively, right? And also quite simple to implement. That's not very important. In practice, there are accelerated versions of gossip that you can use, but I'm just going to skip that. So this is the non-private version of gossip decentralized SGD, right? So how do we make this private? Where it's simple, we can simply add Gaussian noise before we gossip, right? So the private gossip averaging version is the same as before, except that we add Gaussian noise to the local value before doing the gossip averaging with the neighbors. And then the private gossip-based decentralized SGD is the same as before, except that we call private gossip averaging instead of gossip averaging. Okay, so super simple, and here there is this dependence on the sensitivity as always. Okay, so the contribution is not this, of course. This is kind of very easy extension to make the algorithm private, but now the question is, what kind of privacy guarantees can we improve in our relaxation of network? Okay, so this is one of the main theorems. So this is the privacy for private gossip averaging. So what I'm going to show is that essentially first I'm going to analyze the privacy guarantees of this algorithm, only the averaging part. And then it will be easy to extend the privacy guarantees to that. Okay, so for gossip averaging, what we have, so something that is very nice, I think, is that the privacy guarantee of B with respect to U, we have like a closed form solution that is actually exact. That is a little bit ugly, right? So this is not very intuitive, maybe, but this is something that we can compute. So if we know the graph, if we know the gossip matrix, we can compute this numerically. So that's nice. And then what we can show to get a little bit more intuition is that we can show that this is upper bounded by a quantity that depends on the probability of a random walk starting at user U to get to user V in k steps. Okay, so the privacy guarantee essentially gets better with a certain notion of distance in the graph, which is the probability that doing a random walk with respect to the transition defined by the matrix W, that right, you get from a user U to a user V in k steps. So of course, this will be larger for nodes that are closed, hence worse privacy guarantees, and it will be smaller for nodes that are far away, hence better privacy guarantees. Okay, so it really captures this notion of distance in. It's quite nice. It's an upper bound though, so in fact, in practice, if you want the best result, you should use this more ugly and not very interpretable formula. But this upper bound gives this intuition. Okay, that's nice. Then we should based on this, we should, as always, try to look at the privacy utility trade-off, right? If we fix a privacy guarantee, what kind of utility can we get to be able to compare? So recall, so this is for gossip averaging. First, again, focusing on just the task of averaging. I mentioned before that we had this, right? For central DP with a trusted curator, we had this with a 1 over n squared. This is what we would like to get. And then local DP, we had only 1 over n. This is what we want to improve upon, right? So this is the kind of thing that we get. So here, this is a little bit of explanation because now I need to compare an algorithm for which I have personalized privacy guarantees. The privacy that I achieve is not the same depending on which pairs of node I look at, compared to these guys, which ensure like a uniform guarantee for everyone, right? So to be able to compare, so there is, right, it's not so clear maybe how to compare. The way that we found is to look at the mean privacy loss. So this is how much a user V learns on average about all other users U. And then I constrained this loss to be uniformly bounded by epsilon for all nodes. This is the one way we found to compare with these results. And if we do that, this is what we get. So this is again the utility, so directly comparable to this. This is for an arbitrary graph. This holds for any graph that you choose, as long as it is connected. We see that we get exactly the same as central DP up to a factor d over square root lambda w. So d is the maximum degree in the graph. So this says if there is a node that is connected to many, many nodes, there's not going to be too good, which makes sense because this node is going to absorb a lot directly information from many other nodes. And this lambda w is the spectral gap of the matrix. This measures how fast information mixes in the graph. And so here, so this is a measure of connectivity, or let's say a measure of mixing. If you know about mixing time, this is exactly the same of quantity. So this is saying how fast information propagates. Okay, so in a way, what this says is that you would like to find graphs that don't have such large degrees, but still where information propagates well. And so then you can get the formula for a specific graph. If you take the complete graph, this is bad, right? Because complete graph means I will observe all the messages from all other people. D is equal to n. It mixes very well, but the degree is very large, right? And so I get back to local DP, not good. Note that with the random walk, I was happy with the complete graph because it was a different algorithm, right? I was passing things around, yeah.
Can we consider that W change over time?
We can, so I'll get back to this in a second. Yes, very good question. I'll get back to that. Conversely, if you take a ring, this is bad too, right? Now, the degree is constant, so it's good. But it mixes very bad. It takes a long time for information to propagate. Therefore, I need to do many iterations before I converge. And so this, again, I'm back to local DP. That's bad. But luckily, there are graphs that are both mix well and have small degree, and in particular, graphs from the expander family. So typically, expanders have degree of order log n, and this quantity of also order log n, meaning that they make this ratio constant, and therefore, up to constants, I recover with such graphs the utility of central DP, and so I'm happy. And I'm, in fact, happy for a second reason also, is that these graphs are exactly the one that we want typically for decentralized algorithms to be efficient, right? Because the point of decentralized algorithm is that nobody should communicate with too many other people, because that's going to be costly. And I want information to propagate fast, right? And so expanders are exactly the graphs that I would pick, even if I didn't care about privacy. So I'm quite happy about this because in a way things align here and nice. Thanks for the question. So we do have extensions to time-varying graphs. So you can analyze this kind of algorithm for time-varying graphs as well. We have a general result that holds for that. And in particular, this allows to consider randomized gossip algorithms, which is an algorithm where at each step, there is only two random connected nodes that do an update and exchange information, which leads to asynchronous algorithm because this thing can occur kind of asynchronously and in parallel in the graph. And using this, it's nice because we remove the dependency on the degree. So with randomized gossip, things work well on the complete graph, for instance. Again, because now there is not anymore this synchronized communication with all the neighbors at the same time, but there is more a sequence of pairwise exchanges. Okay, I will now move to the conclusion. So this is the extension. So this was for averaging, but this was also for the decentralized SGD case. Maybe do not look at this ugly theorem. The point is that the same happens for decentralized SGD. We have a term in the objective that is the same as the centralized case. It's more like the optimization error. And then the other term has exactly the same form as for averaging. And therefore, again, if we take expand the graph, we cover the privacy utility trade-off of centralized SGD up to log terms. So the whole time I also hide log terms in there. So you still pay some log factors, but they are quite reasonable. Okay, so what happens in practice is that thanks to this analysis, you can show that users get local DP guarantees with respect to their direct neighbors, because the direct neighbors will observe everything if you keep the graph constant. But they get much stronger guarantees with respect to other users. And this is what we show here for different types of topologies. This is the LDP loss, local DP loss. And then based on the distance in the graph, we see that the privacy loss gets better as we get further away in the graph. And the graphs that work nicely are these, for example, the exponential graph or random geometric graphs that are kind of good expanders. Something else that is interesting is that so we think that it fits nicely the expectation of users in some use cases. For example, if you do computation on neural networks, maybe you can expect that users are fine with revealing more information to their direct neighbors, maybe because they are friends or family members, but they don't want strangers to know too much about them. Then you get this by design, right? So this is showing the privacy loss of a node in this cluster with respect to all other nodes in the network. This is on the Facebook ego graph. And we see that, okay, there is local DP with respect to the guy in the community because they are directly connected. But then as you go to other communities, the privacy loss reduces a lot. And it's close to zero, meaning that this guy won't reveal almost nothing to himself. Okay, and finally, something important for machine learning, which again connects to this time-varying graph. So this can be seen as a limitation, maybe the fact that we only have local DP guarantees with respect to direct neighbors. But you can overcome this by changing the graph at each iteration. And so in particular, if you randomize the graph after each local computation step in decentralized SGD, so you compute a gradient, and then you do gossip over some graph, then you compute another gradient, and then you randomize the graph, so you change the neighbors. If you can do that, then it's nice because you can make the privacy loss concentrate more. So instead of having a high loss to direct neighbors and a small loss to people that are far away, since you randomize, you are kind of making things more uniform, and so it looks like this, right? So in practice, this is the local DP loss. When we do this randomization, this is the distribution of loss for a given user. We see that they are all much better if we do that than the local DP. And the more users you have, the better. We know that this amplifies with the number of users, and also the more they concentrate. So we think for machine learning, it's quite nice because we naturally do several computations. And so we can randomize the graph to get better privacy guarantees with respect to everyone, not only with respect to people that are far away. All right, let me just conclude. So maybe the take-home message is that decentralized algorithms and decentralized optimization for machine learning, for instance, can amplify differential privacy guarantee. And we think that this is nice because it provides a new incentive for these approaches beyond the usual motivation, which is more like scalability. And the things that we are looking at are, so this I think connects to your question. For random walk, so far we only have like guarantees for the complete graph, but we are actually working on extending this to arbitrary graphs, and also potentially with multiple walks, multiple models that walk in the network in parallel. So this is for the random walk models. And there are things also about refined analysis to capture the redundancy in gossip-based communication, something that we are not currently doing in our analysis. It's a bit more technical.
So we restart. Now it's my pleasure to introduce Sonia Ben Mokhtar, which is a CNRS research director at the Lyris laboratory in Lyon. And she's head of the distributed system and information retrieval group, DREAM. She obtained her PhD in 2007. She's not so long. And at the University Pierre and Marie Curie, and she had spent 2 years at the University College London. Her research focus is on the design of resilient and privacy-preserving distributed systems. So Sonia is very well known in the domain. Thank you for accepting the invitation, and the floor is yours.
Thank you very much. So thank you very much for the invitation. It's my great pleasure to be here with you today for this workshop. And I will be talking about, I will sort of try to make a pledge towards more decentralization in online services and in today's web. And I will try to convince you that in order to do that, we need to work on decentralized learning, not only, but on decentralized learning. Okay, I'll skip the presentation because Karen already presented me. Just to say that Lyon is a beautiful city. If you want to visit, you are very welcome. Right. So today's online services look pretty much like this. You have users accessing online applications through a variety of devices. And these applications rely on remote infrastructures like cloud or data centers. And these online services, I mean, among these online services, you have, I'll take numerous examples and try to explain basically the threads that are open in these services. So one of them is web search. Of course, web search is used by millions of users every day. The most well-known search engine is Google. And when these services are used, we actually agree on the fact that many of our information, private information, for example, in the context of web search, our past queries are being collected by the search engine, and the objective of the search engine is to provide users, by analyzing these user profiles, is to provide users with personalized responses, but also these like user profiles are used as input for the ad system that is basically at the heart of the business model of search engines. Of course, it's the very same for many of other like online services that also collect user profiles for at the same time personalization and also for funding their or at the heart of their business model. This, of course, opens a number of threats. There is a very well-known scandal that happened many years ago with the AOL dataset. This is an old example that I'm using today. A few years back, like a long time ago, AOL, which was one of the search engines at that time, released a dataset by pseudonymizing the users' names, putting like pseudonyms or just random numbers in front of usernames. And the objective was to help the development of more personalized algorithms for their search engine. And of course, because they thought that, okay, putting just a random number in front of user instead of user identity is sufficient. And of course, there have been many articles, here it was New York Times, that showed that basically it's very easy to get back to the identity of the users by using past user queries. Here, Thelma Arnold was de-anonymized as a 60-year-old lady who lives in the US and so on and so on, has dogs and was looking for a man, single man. Anyway, since then there have been many other papers showing that using this AOL data set, you can actually extract even more precise information about the users, including their interests, their gender, age, religion, zip code, and many other things, right? Another example that we know very well in the team is in the context of location-based services. So location-based services are services that are that use the geolocated data to provide the users with useful information or with a useful service. The most known location-based services include navigation, social networks, video gaming, and so on. And again, these services rely on the fact that they collect personal information. In the context of location-based services is geolocated data. And a study that sampled 30,000 applications from the Apple, random applications from the Apple Store, showed that actually this data is collected by 1/4 or 25% of the applications all the time. And by half of the sampled applications when the application was in use. So this shows that basically location data is also collected massively by companies, by applications. And again, releasing location data opens a number of threats. If you look at these two mobility traces, we can, just by looking at them, infer that you have places that are important for the user, means places where the user stops for a given amount of time. This is what we call points of interest that can be extracted also, obviously, by clustering geolocated data. And then further analysis can allow to infer additional information such as home, workplace, interests like religion, sexual preferences, and so on and so forth from mobility data. Of course, these threats are illustrated by many scandals in the newspapers. Plenty of apps get attacked because the central infrastructures in which the sensitive data gets gathered is subject to attacks very regularly, and leakage is something that is somehow commonplace, right? Every now and then. Why are these attacks very more and more happen more and more? It's because data is the new oil, right? Since a couple of years, as data is being used massively collected by applications for many reasons, of course, for improving their algorithms, for earning money in the context of the ad system, concentrating this data into central servers make basically these companies vulnerable to attacks, right? Because attacking, leaking massive data sets is a source of a lot of money, right? So if we summarize here, these few introductory slides, we can say that today's online services are heavily centralized in terms of governance. They are very data-centric. It's actually at the heart of their business model. And this, of course, opens a number of threats. And besides that, we know that users have an increased awareness on their privacy, as well as the legislator with laws, including the GDPR, but also other local laws here and there that try to push companies towards more transparency and towards guaranteeing privacy, more and more privacy for the users, right? And from this, I would say, observation, I would like to convince you that one of the ways towards which it might be good to go is trying to get a little bit more decentralization in online services. So I also did this claim in front of, in the last Congress, Congrès de la CIF in last June, and this was a drawer that was actually, so it has been captured, that I was also pledging for more decentralization in the web. So what are decentralized systems? So there are many definitions of decentralization or the decentralized systems. like very simply, decentralized system is a subset of a distributed system where you have multiple authorities that control different parts of the system, but no authority is fully trusted by all, right? So you don't necessarily need to put your trust. So you have a subset like of nodes that try to do something together, but you don't necessarily need to fully trust all these collaborating entities. And you have many facets in these decentralized systems that need to be taken care of, including so the scalability, so it's one of the known properties of decentralized systems, but it needs to be implemented correctly. Resilience, because these systems are usually open to many participants, and you have to take care that things are not going wrong in the system. But also incentives, because in decentralized systems, you need to motivate like participants to take place and to play the game in the system. Otherwise, things will collapse, because like if everybody wants to benefit from the system without contributing their fair share to it, it won't work, right? Well, these are some facets, but there are many others. The idea of decentralized systems is not something new. There have been many waves of decentralization over the web. Something that I recall very well is the wave that happened in around 2000 with file sharing systems. That has been followed by many peer-to-peer applications, right? So many users were sharing illegally files over the internet using applications like BitTorrent, Bidonkey, and so on. Tor is still alive for anonymous communication. PP Live is a live streaming application, like a peer-to-peer live streaming application. And actually, the original version of the web that was described by Tim Berners-Lee was also close to peer-to-peer, where he was considering that the web should be a place where each user would be an active editor and contributor and creating and linking context in the form of an interlinked web of links. Nowadays, so if we look at the evolution of the web, so we had initially a web in which you had applications like e-commerce. We had like an access through desktop browsers and so on. The web in which we are today is more social, right, and more mobile. So you have users that access through a variety of mobile devices, a number of applications, and you have social networks that took a huge space in this current version of the web. And the current applications are mostly backed by cloud infrastructures. Many applications, as described initially, are using cloud infrastructures. And since actually Bitcoin and the apparition, the development of blockchain technologies, we are moving slowly towards a new web in which you have a lot of decentralized applications that are being developed, as well as in parallel, a lot of AI-driven services, right? So we don't know where we are going, right? But basically the idea is that there is a new wave of decentralization that has been introduced through Bitcoin and cryptocurrencies, right? I'm not selling that, but it's just a fact. If you have questions, do not hesitate, right, of course. So what I'm going to tell you now in the remaining of this presentation is that, okay, it's nice to try to push towards decentralized services, right? Because we all agree that the centralization that is ongoing with all these GAFAM online services is maybe too much. And it could be nice to think about other services that include at least less centralization. But I'm pretty convinced that there will be no decentralized services without decentralized learning. So why is that? So the main reason for that is that nowadays online services heavily rely on machine learning algorithms. So I saw a presentation by Yann Lequin who said that basically Facebook/Meta would collapse if you remove ML algorithms. There have been papers published by Facebook people showing where ML algorithms are used in their infrastructure, and they are used pretty much, I mean, in many, many places, right? So now comes federated learning that appeared a couple of years ago. Well, the trend was existing in the machine learning community. There have been many works towards distributed learning and so on. But it has been made popular in 2016 by Google researchers that developed this Google Android keyboard application in which they deployed machine learning algorithms on edge clients, like on end users' devices, to train this next prediction word algorithm, right? Since then, as described in many like papers and so on, there is a huge move towards this topic, right? So what is federated learning? Maybe I will use some, I will give you a quick sketch, but you had the presentation this morning by Aurélien, but maybe, repeat some of the things that Aurélien said this morning. Like federated learning works in rounds, in a round manner. So initially, so in the federated learning version that has been initially proposed, you have a central server that basically is responsible for aggregating model updates coming from various clients. You have first a model initialization phase. The server sends an initial model to each client. Clients locally train their model using their local data, and then send these model updates, model parameters to the central server, who aggregates them and then send back model updates to the clients, and then this goes forever, right? I did put small cars because we have a project with Renault, the company that makes cars, that is interested in training these algorithms, these kind of algorithms for inferring the physiological status of drivers, right? Like trying to guess whether a driver is going to have a stroke or something like that in order to prevent accidents and these kind of things. Maybe they will do something with it. I don't know. I don't want to know actually. So I took some slides by Aurélien because he introduces FL very well. Yeah, he did not do it. I thought, okay, maybe I will skip these slides if he does that, but he didn't. So I can just reuse his old slides. So thank you, Aurélien. So FL has a number of characteristics. In FL, you have data that is generated locally. It's usually imbalanced and not independent, identically distributed. So users' data distribution may vary from one user to another. And you have many privacy and robustness issues, right? So you have model updates that may embed knowledge about the participants. This is why privacy enhancing technologies like differential privacy are being investigated by researchers. You have limited reliability, availability of participants. Participants can crash or become malicious and send like bad model updates to the central server. You might have also selfish parties. So some participants can just like do not contribute their fair share to the system and so on. So many threats are open in these kind of environments. Again, this is a slide by Aurélien. You have many I would say, flavors of FL. The most known ones are what they call cross-silo and cross-device FL. In the cross-silo use case is a use case where you have small amounts of parties with large data sets, reliable parties, and parties that are mostly trusted, like running FL between hospitals. And you have cross-device FL, which is basically, which involves much more clients, like in the Google Android keyboard data use case. You have small data third party, limited availability, reliability, and some parties might actually be malicious. And last slide copied from Aurélien is a description of what we call orchestrated versus decentralized FL. Of course, yeah, we saw it this morning in the presentation. The orchestrated version is the one where you have a server that aggregates model updates, while the decentralized one is more a peer-to-peer kind of version of the learning process. Okay, so I will now move to a specific use case. So these are use cases that we investigate in the team. One of them is around the decentralized recommender systems with gossip learning, the one that I'm going to talk about right now. But we also looked at, and maybe this afternoon during the roundtable, we will talk about other use cases. We also investigated FL for improving location privacy in a decentralized distributed manner. And we also explore like private web search mechanisms, decentralized web search mechanisms, and try to secure it with trusted execution environments. And I'm happy to discuss these kind of things with you during the break or this afternoon. And many challenges we try to address here in these use cases. And I will focus in this presentation about the challenge around personalization. So how to achieve personalization in decentralized learning, and specifically in the context of recommender systems. Okay, so decentralized recommender systems. So recommender systems are one of, I would say, the main like online services that we use today. And they are actually in many online services. Of course, in live streaming platforms, like VOD platforms, sorry. In marketplaces like Amazon, eBay, and so on, but also in many other applications. And the idea is that behind a recommender system is that the idea is to get like items recommended by the system based on your past consumed items. So how does it work? So you have users that rate items that they have consumed, and then the recommender system predicts items that a user might like. In a centralized environment, you have many algorithms that are being used. The most basic and most known ones are collaborative filtering algorithms, where basically the algorithm recommends to a given user items that other users similar to him or to her have actually liked, and that the actual user did not consume yet, right? Matrix factorization is a flavor of collaborative filtering, and more recently you have machine learning-based algorithms inspired from matrix factorizations that have been proposed, including collaborative filtering, right? And then in the federated version, so there have been solutions that try to investigate like FL-based solutions that basically distribute in a way algorithms such as collaborative filtering in an FL setting, right? So gossip learning. So we actually try to move these FL-based recommender systems into a gossip environment. So what is gossip learning? As presented this morning by Aurélien, in gossip learning, each node owns its local data and maintains his local model, right? Nodes exchange model updates asynchronously, right? And each node actually aggregates the models he or she received from his neighbors, right? And somehow it acts as a server in the classical FL, right? And there could be many objectives that such a system could try to achieve. The objective could be to train a model at each node that performs well with respect to the user's local distribution. And this is basically, I would call this personalization, right? So the idea is to have, I don't care about training a model that is good for my neighbor. My objective is to, at the end, to get a model that predicts for me items that are relevant to me, right? And you could have another objective, which is training a model at each node that performs well with respect to a global distribution. So imagine, for example, that you are training in a distributed manner an algorithm that recognizes obstacles in self-driving cars or whatever, right? So each user collects videos while driving, right, using the camera that's embedded in the car. And the objective in a distributed manner would be to train a model that is being able to recognize obstacles, even obstacles that I did not see myself, right? Imagine I have never seen a sheep crossing the street, but Aurélien, because he was in Corsica, he saw many sheep crossing the street. So I would like to be able to recognize the sheep when my car, so on. So here the objective would be to generalize as much as possible. And here the objective would be to personalize as much as possible. So in the context of recommender system, the objective we try to reach is more personalization. So there are many properties that gossip learning has. Actually, first, of course, it removes the trust assumption that we have on the central entity, which is also a central point of failure. It scales better with increasing number of clients. But there are many questions that we ask ourselves when we started working on this topic. So, of course, model convergence, even though there have been many works that studied model convergence in a decentralized manner, but we can wonder whether what happens in practice if you have network connectivity problems, network dynamics, device heterogeneity, and so on. Does it work as well or not? Privacy. So the basic question is, does the attack surface increase or is it reduced by the fact of we go decentralized? From Aurélien's presentation this morning, we can actually guess that actually privacy is improved thanks to decentralization. And actually, I agree with him. And I will maybe talk about that at the very end of my presentation with some ongoing work that also go in the same direction. And does decentralization help the resilience against malicious clients, about the resilience against selfish clients, and so on? These are also open questions that many people in the community are trying to address. So the personalization challenge. So I wanted to show you this graph that expresses the personalization challenge that we tried to address. So let us consider a data set. So this data set is a movie recommendation data set called Movie Lens, in which users have rated a number of movies, and it's a classical data set in recommender systems where of course trained algorithms try to predict movies to users, and you actually verify whether indeed these users have liked the movies or not that have been predicted to them. The model used here is generalized matrix factorization. The metric for evaluating the quality of the recommendations provided is the hit ratio 20, which means that we recommend 20 items to each node, and you compute the percentage of items that the user has liked among the 20 recommended items. Of course, the higher, the better. So here, what we did in this use case, we show that if you run the recommender system in a decentralized manner using a classical model aggregation function, what you get is that on average you have 80% hit ratio. So it seems that the users are quite happy with the quality of the recommendations that they obtain. But in practice, there is quite a lot of, there are clearly head and tail users that can be distinguished. So you have you have a number of users here. If you consider 20% of the users that have, we can observe that like tail users have not such a good performance compared to head users, right? There is a large difference between head and tail users. So can we like do something better in terms of the distribution of the satisfaction between various users? So the question that we ask ourselves is, can we improve? At what time did we start? Maybe.
You still have 20 minutes?
Okay.
15 to 20 minutes.
So we started to work on this topic of gossip learning for recommender systems with the focus on personalization. So how to improve users' local satisfaction, and in order to do that, in this use case, there are two algorithms in which we could do something, in which we could have an impact. Is the random peer sampling algorithm. That is an algorithm that allows to change the random graph through which the users exchange their models with their neighbors. I will say a little bit about it later on. And the second algorithm is model aggregation. So when you receive models from your neighbors, how do you aggregate this model with the one that you have locally, right? So I'll start with the second point. So we worked on performance-based aggregation. So the idea is that over time you keep receiving models from your neighbors, but they're not all good for you, right? I mean, with respect to the quality of the recommendations they provide. So in the context of this work, each user had a local validation set to evaluate received models, and by somehow ranking these models with respect to the predictions that they provide to you, we would aggregate them in a differentiated manner, right? So here in the algorithm, we simply assign a weight that depends on the quality of the received models with respect to the local test set, right? So models are first evaluated, and then they are aggregated. Instead of aggregating them with a similar weight, as it is done in Fed averaging, we would actually put a differentiated weight with respect to the performance of the models. So this is very simple. And the second thing is sort of personalized random peer sampling. So random peer sampling is an algorithm that allows to maintain randomness in the graph that connects nodes to each other. And this property is very important because it allows shuffling the neighborhood regularly, which is actually good for privacy, as Aurélien said this morning, but it's also good for convergence. It's also good for the dissemination of the messages over the network and so on. It avoids nodes to be stuck very far away and to see very little from the rest of the network. And in random peer sampling, what happens is that each node selects a node in its view and shuffles part of its view with the one of the selected node, right? There are many flavors of random peer sampling that have been proposed in the literature. Some of them improve resilience to churn to Byzantine nodes and so on. Some of them improve dissemination properties according to the size of the view, the shuffling protocol, and so on. There is a huge literature in this context. And what we do here in this work is that we keep track of the best received models from our neighbors. Like if I realize that Karine sent me a very good model, what I do is that I try to keep her longer in my neighborhood, right? Instead of changing, instead of removing her from my graph. And this is done using a parameter which allows balancing between exploration and exploitation. So if, for example, there is if alpha is high, it means that I would like to explore more. It means that I would like to change my neighborhood much more. And instead, if in like the other extreme case of the spectrum, I would keep a static graph. Like So this is the parameter of the system. So I will.
So you're going to learn more about that client, or that device, or whatever.
Yeah. So basically, this parameter allows to set whether clients want to change their neighborhood a lot, or if they want to keep like stable neighborhood, right?
Yeah, but if you keep the same neighbors, let's say you want to learn more about them.
Yeah, that's not good for privacy, right?
Yeah, exactly. So
Yeah.
that will harm
Exactly.
privacy.
Yeah, definitely. Yeah, it's not
And-
good for privacy.
Yeah, and are there kind of a method that going to control this aspect, or
Yeah, this is a very good question. So for now, what we did is that we empirically tested many ratios, many values of alpha, right? I would say that, but like more dynamic strategies could be good, because at the beginning we could, for example, consider that as I know nobody in the network, I want to discover the most possible amount, larger. I want to discover more nodes, so I would put the exploration value very high, right? So I would like to change my neighborhood very often, and then maybe the more I get a neighborhood that is good for me, maybe the least I want to change, but then I have the privacy problem, so I still want to keep changing a little bit. There's a trade-off to find, but definitely these kind of things need to be explored. And actually, maybe in the last slides, and in our ongoing work, where we are looking more at the privacy aspect, we realized that, of course, the version here of the personalized gossip somehow, of course, leaks more than if you don't do personalization. Like if, for example, you just keep changing the graph all the time, in terms of privacy, it's much better. I will very quickly talk about experiments, because there are many experiments in the paper, and it's kind of useless to bore you with results. Just the idea is to show that we evaluated this work in two use cases: a movie recommendation use case and a point of interest recommendation use case, using simulations, using two machine learning models, one that is more for recommending points of interest and the other one for recommending movies. Many competitors have been considered. The classical, federated, learning algorithms using a central server, including solutions that do meta learning and so on, that push towards personalization, and also decentralized flavors of these algorithms that we implemented, because they did not exist in the literature, in order to have also a fair comparison. We did that also in various data sets for points of interest and also for movies. Maybe one result that I would like to show is about the fact that going decentralized actually improves the tail performance compared to traditional or centralized or federated solutions. For example, if you look at the 90th percentile, so the 10% users who had the worst performance, we actually improve their hit ratio in the personalized solution, right? Even the 50th percentile. I will finish my presentation by discussing some ongoing and future research directions. Of course, in this work, we did not look at all at privacy and robustness. And the question that, of course, that comes naturally is, as a node exchange model updates with their neighbors, how sensitive is that? Aurélien work showed that actually of course, differential privacy can help protecting users in this context, and it's actually better if you do it in a decentralized manner than if you do it in a centralized manner. I will I have one slide describing what we are doing from an empirical point of view in this context. And of course, robustness is also an important question. And one of the questions we are wondering is whether this performance-based aggregation, whether because you test models that you receive locally, whether it naturally protects against some types of poisoning attacks. For example, if your neighbor sends you like crap model, just as you test it, you can just drop that model or aggregate it with very, very small weights. So maybe it helps protecting against poisoning attack. It definitely does not help protecting against like backdoor attacks because these are more pernicious attacks. They don't necessarily have impact on performance, but they have impact on they have triggers that would still be bad for robustness.
Excuse me. Another question maybe to you and to now. So in the case where you have the sequential, like the graph, the communication between the nodes, when you have this bad model, do you always have this choice to take it or to drop it, even in the sequential, or in the case of presentation, for instance?
I mean, in our case, as somehow the aggregation is decentralized, it's always at the end, it's a local decision, right, that you take. You receive models, you can always decide whether you want to aggregate them or not, right? So, but how to take this decision? So there are many works in the literature that try to, for example, not only by using the performance of the models, but by using by looking at the properties of the model itself. There are solutions based on median in order to exclude outliers. If a model looks really different from the model that you usually receive and so on, you just decide to drop that model. And these are works that are done in Byzantine resilient aggregation, like model aggregation functions. So it's always possible to drop.
So even in the random walk, would you find?
I guess I don't think we'll explain.
Okay.
In this, in principle, the setting is a bit different. I guess here there is personalization, so you're not trying to on the same model for everyone.
Yeah.
So how would the sequential algorithm work under personalization?
Yeah, it's clear, but I was just wondering about the random walk phase, let's say, or way of learning. Do you still have this choice to drop such bad model, or because you kind of, you're receiving a model from another node, so.
Yeah, no, that makes sense. So in what I presented, no, we're not doing this.
Okay.
You could consider doing it.
Okay.
Yeah.
Actually, it's two complementary concerns. The privacy concern and the robustness concern are two complementary concerns. Usually people look at them separately. They start to the community is starting to look at this problem simultaneously, right? Yeah. But sometimes it's really contradictory, right? Mm-hmm. So there are recent works on this. Exactly. So on the privacy side, one of the recent things we are trying to do, so we developed an attack in which, a client in the context of a recommender system tries to learn his most similar users, try to cluster users somehow, right? For example, in order to discover communities. If I am an attacker and I create, an LGBT profile by liking only LGBT-related movies, for example, can I discover in the network the other users that have a similar profile as mine, right? So basically here in this case, users are considered honest but curious, meaning that they just observe whatever they receive from the network. They compute a ground truth based on the top K most similar users to them, kind of in a centralized setting. And what they try to do is that each time they receive a model from their neighbor, they try to evaluate its similarity with respect to a locally trained model. And at the end, there is a comparison that is done between the ground truth that users have computed and the top K computed by the users through the interaction with the networks. The only thing that ongoing results actually show that, of course, in the centralized model, the attack works very well. So central server can leak a lot of information about users and can reconstruct all the clusters based on the user's preferences. In a decentralized manner, it doesn't work very well because what we call model dilution, and it's the very same. I would say observation that Aurélien described earlier, and he backed up this with the DP study on how DP could be applied in this context. The idea is that the central server, somehow when he received model updates from clients, the model parameters are not diluted. They are somehow pure because the user just updated the model and sent the model update to the server. While in a decentralized manner, what happens is that when you receive a model update from your neighbor, this model has already aggregated many other models in the past. And somehow you have your model parameters that are somehow diluted. Your preferences are somehow diluted with the preferences of other users. So it's a sort of natural noise that is being added with respect to your own preferences. And it's much more difficult for attackers to run attacks and infer information about users. So we are trying to push in a study in this direction using various attacks. Various attacks. So here comes the conclusion. So I hope I convinced you that today's online services are too centralized, and that it's important to work on trying to decentralize these services. There is a new wave of decentralization that is undergoing on the web that has been launched with this blockchain thing. In order to really achieve really devise new decentralized services, it's important to work on decentralized machine learning. But this opens many challenges that are related to many research communities. Of course, machine learning, optimization, distributed systems and algorithms, security, privacy, networking, and so on. So it's important that these communities somehow, all the communities address these kind of problems individually, but also sometimes by working together. But it's not always easy, but it seems important. And it's also important to understand the benefits and limits of decentralization. Why did previous decentralization waves fail? Because we had this peer-to-peer trend in the 2000, but actually it was killed by nowadays centralized online services. Why would it work this time? Does decentralization really increase or reduce the attack surface? It's very important to carry out research in this topic. Is it possible to enforce at the same time privacy and resilience to Byzantine nodes? And what can we do beyond empirical works? This is a question I ask myself because I do a lot of empirical works, but it's important to always to try to somehow to see whether we can. Of course, to simplify the image, you have sometimes very theoretical works, sometimes very empirical works, and maybe the truth is somewhere in between, right? Trying to combine both to get nice results. Yeah.
Okay. Thank you.
So I will be talking a little bit about the Jamal. So initially, what I thought was to talk about state of the art, basically. But then I thought that will be a little bit boring for everyone. So I try to mix between. There is an echo coming back. Maybe.
Just. Test.
Yeah. So I try to mix actually a sort of a talk combining both some related work, description of related work, and some work that we are currently doing just to illustrate this concept of edge machine learning. So just before I go to the talk, in fact, I'm based now in TII, Technology Innovation Institute. The institute is an R&D research institute where we are actually trying to combine, to do some research, but also to apply the research that we are doing. So we are not sort of an academic research center, but we are more in R&D. So our work needs to be justified with some development and needs in the industry so that we can do the research. We have 10 research centers. That's just the second slide, the only slides I have about the TII, because most of you, I'm sure, don't know TII. So we have 10 research centers currently, and we are working on different aspects, going from quantum computing, propulsion and space, directed energy, material robotics, and security, all these aspects. Myself and my team, we are in the Digital Science Research Center, and we have 3 units. One is about security, the second one is about telecom, and the unit where we are is in the AI unit, that is a cross-center unit. That's just a quick introduction of the institution where I come from. For the outline, so we'll be just quickly giving a quick introduction. Then I will be providing an overview of the edge machine learning, what we are calling the edge machine learning. Then I will be discussing an example of what we are doing on the edge machine learning, that is the human activity recognition. Then I will talk about some research directions and future work for those who are interested in the topic. Yeah, just before again I go deep into this discussion. So back in June when I joined TII, so we were actually, the initial plan was that we work on what everybody is doing today, is basically using GPUs, clusters, doing a lot of computation and this kind of stuff. We have even like a supercomputer coming soon. So we started planning that and this kind of stuff. But then there was this need that came on doing machine learning on the edge. So that's the complete opposite of what we were used to do. And that's interesting, actually. I was extremely curious to see what we can do with this kind of stuff. So it was not, I have never done that before, but it was so exciting. We always think about doing the computation in a bigger and bigger sort of resources. But then this actually pushed me and pushed us, actually, everyone, to think of what happens if we go to the small devices, right? So do we just ignore the small devices? I mean, just say simply that we cannot do machine learning in that. We keep them just for data collection. And then we ignore what's happening there. The most important thing is that the computation happens in the cloud, and the cloud at the end of the day can be infinite in terms of resources. So I was really excited with this topic. So we started working on that, and that's what I will be discussing during this presentation. So when we talk about the edge, it is important to mention also the cloud. Okay, the edge doesn't, in my opinion, wouldn't exist without the cloud. So there is this sort of a collaboration that needs to happen between the cloud and the edge to fulfill a certain number of needs. We focus on the edge just to demonstrate the importance or the interest actually of the edge, the value that the edge can bring. But at the end, you will see that I will make a point that these two should be working together. So just for a common understanding on the cloud, so the general definition we have is that the cloud computing is the in-demand availability of computer system resources, especially data storage and computing power, without direct active management. So you don't basically care about managing the servers, but you care about the resources that you get, and that's the most important thing. Well, the second thing is basically coming to push a little bit those resources close to the user. That is the edge computing. So we want actually to keep the data, instead of sending the data back to the cloud, we want to keep some of the data, or all of the data, close to the user so that we compute it directly. That's interesting, for example, in the real-time application. And then we have the other part, that is the machine learning. So here what we want to do actually is to extract some patterns and some value from the data that we see every day, that we collect and see every day. So the idea here is the edge AI is coming, or the edge ML is coming actually to combine the power of the edge together with the benefits of the machine learning, so that the processing can be done on the edge directly. So I find this illustration very simple, but very interesting actually to at least position the space in which we are. So you have the cloud computing that is out there, that's a sort of a centralized ecosystem that is collecting all the data, and then thanks to the computation power, it can do whatever we want, at least between quotation, whatever we want. And then on the other side, you have the edge. So I'm providing this figure because it's very important to understand where the edge is. Depending on the community of the researcher or the developer, so the definition of the edge can vary, right? So, and we need to put a sort of a clear definition on that. So the edge from our side, we think of edge, it's almost at the extreme edge, I would say, okay? So independently of the sensors, the individual sensors, our edge is starting from this, right? So an edge device is any device that has a limited set of computation resources, but can operate some functionalities, basically. You will find also some definitions where you have we will call them later edge servers, actually, at this level, where the devices actually are highly performant. They have GPUs, they have a lot of memory, so on and so forth, but they are still edge. I mean, the people, they call them edge because at the end of the day, they are not the final destination of the data. So we put them in between the small devices and the cloud servers so that we can do some processing in an efficient way. For the moment, we are actually handling this part of the edge where the devices are limited in terms of resources, and we want to do some advanced computing and advanced processing from the machine learning perspective. So in terms of motivation, so why are we doing this kind of things? So the small devices, we see them today, they are everywhere. So I guess everybody has a small smartwatch. We have maybe a couple of phones, at least. Some people, they have smart shoes also, smart glasses coming slowly. So you have these things that are becoming sort of a must to have for everybody. And then you have the connectivity. The network is becoming somehow cheap, and all the devices are connected together. So the situation is that we are collecting a lot of data. I mean, we already had a lot of data, but the data is increasing with the devices that are getting connected every day. On the other hand, we have huge privacy and security issues. I think the talks we had this morning, they were focusing on these specific things. They very interesting talks, by the way. So everybody is scared about what could happen if the data goes somewhere, and then we analyze it, we find we sort of extract some private information. So you have a lot of constraints that apply on the data transmission nowadays, and you have the computation power that is available at the IoT scale devices. Things are really sort of moving forward, and you have a high demand in terms of data. So I have my data even at the end user level these last years. I have my data. I don't want anyone to touch my data. I need to know what's going on in my data, so on and so forth. So these observations, actually, they push researchers and industry to think of increasing the power of the edge with capabilities that will allow performing the machine learning directly on the edge. So the data should not be transmitted to the cloud before doing the edge. This is the case of the federated learning that has been presented this morning, but we have other paradigms also that help us in doing such a thing. So we get into, I try to illustrate this what we have said before. So this gives birth to the AI on the edge, or the edge ML. So basically either we do the machine learning on the edge, or we build the machine learning. So in the community, that's what we tried actually to formalize these last 6 months. We have people talking about the machine learning on the edge, or the AI on the edge, and we talk also about the edge ML, right? So the AI on the edge is basically trying to see how can I execute my previously or usually big models, big machine learning models on small devices. On the other hand, you have the HML that is coming actually to ask the question on how can I build models directly on the edge. So remember, the edge for us is a limited resource device that needs to be taken. I mean, this is a constraint that needs to be taken into consideration. This takes us to the HML in general. That is sort of encapsulating both of these concepts. So the edge machine learning. So what is it? It's basically a combination of edge computing and machine learning. It is aiming at building and executing machine learning directly on the edge devices for both operations. It can be operated either on a single device or multiple devices. It is constrained, but one of the most important thing, actually, this is what is pushing everyone to think about this distributed learning and edge machine learning at the end of the day, is that we do not want to share the data. Data has to stay where it has been collected as much as we can. And then you have communication constraints also when you are sending the data back to the cloud. What we are expecting from this edge machine learning is that we should obtain comparable quality to the cloud operations or to the cloud-based machine learning, better privacy and security. This is by construction, I would say, should be a benefit. It's not granted, but should be a benefit. We expect also to have a lower latency because the data is not sent back to the server or to the cloud, and the answer is not transmitted through the network. So you do the operations locally, and then you offer offline capabilities because again, since you are supposed to have everything on the local device, you do not need necessarily to have a communication, which means you don't need to have a connection at the end of the day. So these are examples of questions that the edge machine learning is trying to answer to. The first one is there a real need to let the data leave the edge device? For the moment, there is. I mean, till few years back, there was a need, in fact, because the edge was very limited in terms of computation. But now we start asking the question because the devices, the edge devices, they started to get much more interesting in terms of computation power. So I think this question is valid, and I would say the answer is that there is no hard reason to let the data leave from the edge to the cloud, unless if there is a cooperative work that we can also always consider. How can we allow a training to happen directly on the edge? Again, you have your data on the edge, but the observation also is that you do not have all the truth. So there should be a way to build methods that would help us to build directly the models on the edge, and then how to efficiently execute the models on the edge. If I have an interesting model, it doesn't mean that I should just keep building my models on the edge, otherwise I will not use. I can always exploit what has been done, but I need to find a way to adapt such models to the edge. The edge comes with requirements. The HML comes with requirements. The requirements, they combine actually both the requirements for the machine learning and the edge computing. You have different requirements. Obviously, I will not go through all of them. But for the machine learning, you are expecting a high performance, the operations to be done, as fast as we can, at least when building the model. This is why we are using high computation power. It's important to think also about the inference. We want to do the inference very quickly. Machine learning is supposed to preserve the privacy, but the last years we understood that machine learning can be used actually to sort of reveal private information. So that's an important thing. Labeled data and dependency. Well, we have more unlabeled data than labeled data. So it will be interesting to have models actually and methods that are able to rely on unlabeled data to be able to extract patterns and build models. The edge computing requirements, while you have the computation efficiency, we're expecting that the computation is done much faster, for example, because the computation is closer to the user. So you are not, for example, sharing that computation with many users. So it should be much more efficient. The bandwidth, we communicate less. So we should have that communication going faster than if we were in the in a cloud environment. Then you have the offline part, as I introduced it before. So here you want to run your services without depending on a distant machine or a cloud machine. And you have something that is related to all these. I would say these are the overall requirements. You have the energy consumption and the cost optimization, of course, that comes with everything. So cloud computing, the promise of the cloud computing was basically to reduce the cost, but edge AI is supposed to reduce the cost even more, because we are not sort of requiring those big computational resources as we do in the cloud. All right. So the next step, next part of the presentation, I tried actually to summarize one of the papers that we have written here. So we started working on it back in June. The paper is a survey. Actually, it's a very long survey. It's around 50 pages, but I tried actually to just sort of compress it and provide a very high level discussion on a few methods, just to introduce the audience a little bit to this edge machine learning world. So I'm not intending to give all the details for all the methods. I would be happy to share the paper if needed. I think every topic would need 1 hour presentation if we want to go into details. So I will just give sort of a flavor of the methods that we have, or the models, the paradigms that we have inside, before moving to an example application that we are doing here. So the paper discusses actually 3 parts. So we have the inference in the edge, we have methods for that, we have the learning on the edge, and we have the data pre-processing on the edge. So all these parts actually, they are blocks within the machine learning life cycle or process, I would say, and specific methods are proposed for each one. For the inference on the edge, so we are considering actually 2 aspects in general. So you have how to use large machine learning models on the edge devices, and then how to increase the inference efficiency. So these are the 2 questions everybody wants to answer to when you are dealing with the inference. So you have a model and you have a device. So how are you going to execute, or what are the steps that you need to perform to execute those models, right? I'm not saying here that all the models should be, the edge should be able to execute all the models, but you have models that could be transported to the edge. For this, you have 2 main categories of methods. So you have the model compression and approximation, and then you have the distributed inference. Again, the paper details everything, so I will be trying to give some ideas on this part. So for this family of methods, what we are trying to do is actually to reduce the size of the model, to adapt it to the constraints that we have on the edge side. Well, when we say that we want to reduce the size of the model, necessarily we are taking the risk that the quality of the model may deteriorate, okay? Then it will become a sort of a trade-off between the quality that you are getting and the size that you want to get from such an operation. And you have also the constraints of your specific devices that you are using. You have 3 main families of or subfamilies of these methods. You have the quantization, you have the weight reduction, and then we have the activation function approximation. So these ones, they go in the different layers of your neural networks. We're focusing on the neural networks here. So just to give you an example of what we mean by this. So for the quantization, what actually we are trying to do is a sort of changing the representation of the parameters, right? So I'm not sure if people are familiar with the small precision methods. So we are trying actually to move the parameters from one representation to another one, so that the space we are using in terms of memory is lower, and then the computations that we do are much more faster. So we go, in general, we go from the floating point representation to an integer representation, so that, again, things are supposed to go much faster. You have the figure on the right here that I took from from NVIDIA, and it explains very well the thing. So you have your actually distribution on a floating axis, and then you want to bring it actually to an integer axis. So of course you will have different issues that will come with the data when you are losing precision, basically, but you are increasing in terms of performance when you are coming to small devices with limited computation power. So you have different types of quantization, again, that we have detailed in the thing. So depending on the representation that you are sort of targeting, depending on the number of, let's say, I would say the length of the interval that you are targeting, the number of bits that you want to use to represent the data. So different methods apply for such kind of things. So here I'm listing a little bit some examples of work that has been done in the near past, I would say. So the best representation that I was looking at a paper like a few days back, and it was clearly demonstrating that anything that goes below 4 bits representation becomes useless. So you have some work that goes below the 4 bits representation, but there is no particular sort of interest compared to the other. So the best representation that has been found is the 8 bits so far, but well, the transformation needs some time. So that's interesting, actually, because again, we are looking at this problem only from the side of limited computation power on the device or on the edge device. So we want actually to reduce as much as we can, but models like this one will start actually deteriorating when the data becomes more complicated, for example. Again, I just saw the paper a few days back, so I need to look into that a little bit more. The second subfamily, I would say, so I keep moving my mouse because I have this thing on the screen. So the second method is actually the weight reduction or the pruning. So I give you a figure actually just to illustrate the difference between the quantization that we have discussed before and the pruning. The quantization is actually keeping the same, I would say, architecture and the same dimensions, but it is changing the representation of the data. The pruning is doing something else. It's actually removing some of the parameters of the model. It can be a node. It can be sharing, for example, specific parameters that are redundant, so on and so forth. So the size here, even the size of the model in the weight reduction may completely change. Okay, so that's the interesting part. The model is simplified more, and it suits more actually what we are trying to do in terms of edge machine learning. Again, I try to mention here some results. The parameters, actually, you have some work that has been done reducing 35% of the parameters, and these initiatives actually are very interesting because it's basically, most of them, they tell us one thing, is that if your model is big, it doesn't mean that it is really good, right? It's not the best at the end of the day. So there is a room to improve better. If you see the first work, they have done an excellent work. Well, the application was on a specific area, but the results are very promising in the sense that you reduce 35% of the parameters that you are removing, and you lose 2.2% in terms of quality. So this is an interesting sort of result when we think of moving our models to the edge, to your mobile phone, for example, or your smartwatch. So the interesting thing of the weight reduction, so we reduce the model size, we remove the uncritical parameters, or we do a sort of sharing of parameters. We use less memory because we do less operations. We reduce the task latency because you will do basically less search and less, I would say, fine tuning at the end of the day. You improve the computation resources efficiency, and then you optimize the energy usage at the end of the day. Then we have the distributed inference. Here, instead of reducing actually the size of your model, what we are trying to do, what the work is trying to do, or the efforts in this area, they try actually to see how to distribute this inference. The inference will not be executed on one device, but several devices will be actually collaborating together to just do the inference. Again, this opens sort of the door to many options that you could use, many protocols, many, I would say, scenarios that you can think of, many questions that you could answer to. But the most important thing to understand here is that you are distributing, and a device can be, for example, specialized in a specific class, if you want. So, and then the new instance that comes can be sort of can visit different devices to see the percentage or the confidence of the prediction. So the distributed inference divides the machine learning models into different portions, and then puts them in different devices. Three ways of looking at this problem. So you have the local processing on the edge device. So things will be done on the edge device, or you will connect your devices together, and then the new instance needs to travel, either to travel or have a sort of a pre-processing so that you decide to which edge device you want to sort of direct that specific thing. And then you have a third option, but here we need to introduce the cloud. We divide actually things between the cloud and the edge itself. The challenges is basically how to identify the portions. How are you going to divide your model actually in the best possible way, and where are you going to locate those parts of the model, and then how do you manage the data exchange between the devices? From the experience I have on this kind of things, this is very interesting, but somehow it goes against what we wanted to do, in the sense that the data should not leave the device, right? So now, if you are collecting a device, you are collecting your data, your own data, and then to be able to predict something on your data, you have to give it to another device. This goes completely against our initial objective. But then you have scenarios where this applies, and this makes totally sense. You have other inference acceleration techniques. You have the knowledge distillation. Again, you are learning a big model, and then you are trying to specialize somehow the model on specific cases or smaller cases. Here, you are taking advantage of something that is built on the cloud, and then you try to exploit it on a smaller one. So the second one is the activation approximation. As I said in the beginning, like, the paper is very long, so I try to summarize it as much as I can. So the activation approximation, so you are trying actually to replace non-linear activation functions with the simpler ones, so that the computation that will be done on the device will be simpler and faster, I would say. Then you have the early exit of inference. This is what I'm putting here on the right as a figure. So we're trying actually to find ways not to use all the model when the new observations to predict they come in the network. So we try actually to find a way to find exit ways if we can, so that we don't take all the observations until the end of the network. This is an interesting actually method for the inference. And then you have the cache. Everybody is familiar with the cache, like for applications, it is a very similar principle. It's basically trying to understand the queries that come to the same device that is located somewhere, and we try to cache that so that the next, I would say, request, we assume that the queries that come are similar in a specific area, so we can find the answer directly on the device or in the cache without deploying a lot of resources for the computation. So for the inference, you have a variety of methods that are there. I think we talk a lot about the compression and the quantization, but we have plenty of other methods that are there. There are promising results, but I would say that the implementation is problematic on this side because we have sort of very specialized implementations that are done so far on very specific devices. For example, most of the hardware manufacturers, they work on that, but they work on their specific devices. You do not have methods that could apply directly, I don't know, for real public devices like mobile phones and this kind of stuff. So there is a lack of automation. So once we get inside, there is everything to be done in a manual way. So if you do on a specific device, then you have to redo completely from scratch on other devices. There is no killer application yet that has demonstrated that these methods, they will be useful. So there is still work needed even on the inference side. I'm sort of insisting on this because when we attend different talks and this kind of stuff, we assume that the inference is done and we have done everything on it, which is not the case, right? So there is a lot of work in terms of industrial implementation and concretization of this inference on the edge that needs to be done. So I think it is sort of going too far saying that this problem has been solved. I believe that there is still a lot of work to be done. The second part is the learning on the edge. Well, here we said that we want to build actually the models directly on the edge. And this question is extremely important actually, and the point makes sense because again, so we were relying the machine learning or the edge machine learning definition that we had even a few months back, everybody had was the inference, how to do the inference on the edge, right? But then if you want your data to stay on the edge, you need to build your models on the edge. Otherwise, you have to transmit your data at some point, at some stage. Your data has to leave the edge and go to a server, be it on the cloud or somewhere else, but it has to go somewhere. So we see more and more efforts towards this topic of building the models directly on the edge. I think, again, we will encounter the same issues as what we have discussed on the inference, which means you have some models that have been implemented on specific devices, but then you have all these issues of automation and then going to scaling up and these kind of things that are there. So we are supposed to rely on locally stored data, and then you have plenty of other approaches. You have more than what I have listed here. You will see later on in the taxonomy that I will provide. So you have the distributed learning. As we have distributed inference, we have distributed learning, we have the transfer learning, the meta learning. You have so many other categories, but I will be just describing the first two, and then I will refer you again to the paper to eventually read more. So the distributed learning is a family of methods that are actually trying to build the model in a distributed and cooperative way. So we divide the training data into, or we assume that the data is already distributed, and we try to build the model locally, and then you have a server that is coming to aggregate everything. So I guess everybody understands the reference to the federated learning that has been described deeply this morning. You have two approaches in general. You have the client-server approach. This is what we mostly use, and the federated learning most of the instances of federated learning are based on this implementation, and then you have the peer-to-peer approach. So the client server, again, you have small servers or small machines, devices that are computing local models, and then we communicate with the server that aggregates those parameters, and then it shares again the general path, the general model that it has, and it iterates until things converge. The peer-to-peer approach, on the other hand, is actually doing a different thing. You don't have a centralized machine. The peers are discussing between them, and then it rotates. Actually, the construction principle rotates on the different devices so that everybody participates in the construction. So we can distinguish three approaches for this distributed learning. You have the cloud-enabled distributed learning, the edge-enabled distributed learning, and then you have the hierarchical distributed learning. So the cloud basically is the classical thing that we are discussing. And I believe that this has been the topic this morning. So your devices actually are doing small things, and then they share with the cloud aggregates and sends back the thing. On the edge enabled, again, here you have what we call an edge server, right? An edge aggregation server. So it is not on the cloud, but still it is close enough to the edge devices so that we call it actually the edge server. So the devices are sharing the data with the edge server and not with the cloud. And locally, they all work together to achieve to build the model. And then you have the other part, the third category, that is the hierarchical distributed learning. In this case, you have a mix of edge servers and cloud servers. That's an interesting approach, actually, when you are facing different issues in the data, the unbalanced classes, for example, the non-IID data, the diversity of devices in your infrastructure, for example. What we are doing actually here, we have sort of clusters of edges. Some devices are connected to a specific edge server, and then the one that does the aggregation first is the edge server to do it on the edge devices, and then all edge servers, they share with the cloud the version of the model that they have to be able to build a bigger model. All right, so instances of distributed learning. So you have federated learning. The two talks of this morning, I think they presented this very well. On the other side, you have the split learning, for example. Again, when we start distributing, this opens a lot of options, a lot of scenarios. The split learning actually is trying to distribute the model, right? So we're trying to distribute parts of the model to run in different locations. So you can consider like a set of layers or just one layer to run in each server. But again, you have different approaches. But here, the distribution is interesting, but we always need to keep in mind that there is a cost that comes with the distribution. You have the communication, and then you may have to release some of the data that you are manipulating because you may need it in different locations, right? So that's the cost that you need to pay. But in terms of efficiency, it definitely increases the efficiency, especially in our case, which is the edge case where we don't have a lot of computation power. The second type of edge learning is the transfer learning. So here, actually, we are trying to mimic, I would say, the ability of someone to learn from someone else, right? So this is what we call the teacher-student models. You have a big model that is called the teacher, and then we are trying actually to build a more specified model or more specific model to solve specific tasks. We do this a lot in image processing, for example, where you have, for example, you can use most of the existing models, YOLO or whatever, and then you specialize it in your task. If you are working on medical images, for example, if you are working on, I don't know, we have done a project on pollution on the desert, and it was used to be able to identify trash in the desert. We have drones that are scanning the desert, and then we send that to our model. We didn't build the model from scratch, but we just used a version of YOLO, and then we combined it with our data, with the small data set that we have used to be able to learn and increase the efficiency of what we were doing. I see that the time is going, and I still have few slides, so I will just go quickly on these ones. So in the transfer learning, we have mainly two approaches: the layer freezing, and we have the model tuning or fine-tuning. The layer freezing, basically, we want to block some layers, and then we specialize some layers to adapt to the specific specific task that you are having, or specific tasks that you are having. And in the model tuning, you are trying actually to adapt completely the model to handle your small data set that you have on your side. This is just a summary of the taxonomy that we have put in the paper. Again, you see that it's too long to discuss everything. I think every topic needs, again, 1 hour to describe it. But we have tried actually to be as clear as possible. So we have divided into the inference on the edge, the learning on the edge, and we have the data pre-processing on the edge. We have added this part because when we are working practically on these kind of things, we notice that it's not that straightforward actually to do an inference or a learning on the edge without handling the data processing issues that you have. The data has to be captured, has to be cleaned, has to be prepared to do all these kind of things. So we thought that it's interesting to see what kind of things that are done that could be done on the edge, and what kind of methods that are there. So for the construction of the model on the edge, we have seen two types of methods. But then you have the meta learning, where you have the few shots learning, for example, is there. We have the self-learning, we have the multitask learning, we have different types of models that you can find there. Then we have done a quick study on what kind of requirements that are satisfied with the sort of families of methods. I think you can see here that we have a lot of minuses. That is a positive thing, actually, because this shows that there is a lot of work for the community to be done in this field. And yeah, I think definitely there are promising things, but there is still a lot of work to be done to progress a little bit more on this field. All right, so after a quick presentation of sort of a landscape of the machine learning on the edge, I was thinking it could be interesting to share one of the problems that we are trying to solve. This is a problem we have started with, actually. So we were thinking of a scenario where the data could be interesting to build models on the edge, but also we didn't want to spend sort of years before building the scenario, right? That's an important thing, because we could tackle, for example, image processing on the edge, or natural language processing on the edge. But for this, we need few years. And in industry, it happened. I mean, things work in a different way. So if you don't demonstrate that things make sense, you don't get the funding and you don't continue your activity, right? It's as simple as this. So what I will be showing here is a set of tasks that we have done to explore this field. That is the human physical activity monitoring and prediction directly on the edge. This relies basically on three papers. Well, the last one I will just say a word on it. So the three papers that we have done, the first one is some practical insights on incremental learning of new activity, on new human physical activity on the edge. And the second one is a demo paper on Magneto and how it works. The third one is we finished it few weeks back, is handling the catastrophic forgetting of adding new activities directly on the edge. Hello?
Yeah.
Yeah, it's okay.
Well, good. Okay, all right. All right, so activity detection and recognition, that's not a new topic, actually. So we are not trying to reinvent the wheel, but it's good to understand that you have two types of activity. You have the digital activity and you have the physical activity. Digital activity is everything happening on the web. When users are browsing, we try to understand what they are doing, either for the recommendation purposes, like what Sonia presented this morning, or just to monitor what they are doing if you are in a professional environment, for example. Our interest here lies under the physical activity. Again, you have some work that has been done in the past, and we are not sort of claiming that we are inventing anything in this field. But our interest, again, just to keep the focus, is to build something that will recognize this activity directly on the edge. So when you are doing the activity recognition or the physical activity recognition, you have first to collect the data. This can be done in different ways. You have smartphones, smartwatches, you have the UAVs, you have people who use the UAVs, you have people who follow the, who monitor the cameras and these kind of things. They do it visually, that's interesting. In our case, we just focused on having mobile phones, exploiting all the sensors that are in the mobile phones and the smartwatches, and you have honestly plenty of sensors that can be used in the mobile phones, and you have a lot of surprises also when you take things to practice. You have a lot of surprises that come from this let's call them Internet of Things devices that are there that we don't see necessarily when we are when we are working on the theory side. Our motivation at the time, so we have been asked to have these kind of activities because of commercial purposes. We wanted to understand what people are doing so that people could place actually ads depending on the characterization of the activity that they are doing. For health purposes, we have a sort of a collaboration that should be starting this 2023, working on the identifying, for example, the movement that elder people are having, just to check if they are sort of safe or not, like if they are falling down, if they are sort of walking the same way they were walking in the past, this kind of stuff. And then you have the activity monitoring for offensive security for the military purposes, to know, for example, if you are following a suspicious person, you could do that directly on the phone or on the other devices. Why it's interesting, actually, because also all the big players there, they have their own sort of activity monitoring. Some of them actually, when I started this project, honestly, I thought it was not that a huge thing, but some of them, like Google, for example, is even selling the data of the users. The activity data of the users for those who are using their applications, right? So we thought it would be interesting to have our own instead of buying data from other stuff. So how can we exploit actually the Edge AI to recognize the activities without sharing personal data? That's the key thing. We didn't want to send back the data. So the way it is done today is that the processing, all the process is a centralized process. We collect your data on your phone or on your smartwatch, on your smart shoes or whatever, and then the data is sent back to the cloud. So there is nothing that is done on the device except the collection of the data and the display of the result. So the inference is done on the cloud, and then you get your data or your result that is sent back to you. So there are a lot of challenges out there. So you have a lot of number of activities actually that you need to track, and building a model that knows all the activities would be just not realistic, because also you have people who are not concerned with some activities and others they are concerned. So having one model that fits everyone will be a little bit challenging. You have technical issues that honestly I discovered when we have been working on this project. I was always thinking that the devices that are the sensors that are on the devices, you just ask for a specific information and then you get it, and it's of a high quality and whatever. That was not the case actually when we start the implementation and working on the technical side of these problems. You have a lot of unknown activities and you have a huge lack of data. Unless if you buy the data, of course, and then you trust the provider, that will be maybe something that you could do, but there is a huge lack of data. And then the training of the machine learning is computationally costly because we have a lot of data that has been that is generated every day from this kind of device. On the opportunity side, you have a lot of devices that are everywhere nowadays, as we said before. You have things that are coming. You have a lot of also pipelines that you could use, but then these pipelines, they need some adaptation, but still you have them there. You may not start from scratch. And the cloud also offers, of course, a lot of computation power. So this is why we are sending everything back to the cloud. So all the process actually at the end of the day, this is what I'm trying to show with this figure, is that all this process is done on the cloud side. How can we do? We transfer all this process actually to the edge. You have issues with the cloud-based models. So you have the depersonalization difficulties. As I said before, you cannot have one model that fits all. That's a very important thing. Everybody wants to have his or her own results, data, independently of the others. Then you have the communication latency. So if you don't have a good communication sort of network, you will have some issues with that. And then you have the privacy issues, right? The data is transported to the cloud, as we have discussed before. We came up with a different architecture a little bit. On the left side, you have the current way of doing this kind of solving this kind of problems. Everything is done on the cloud, and things are communicated. The data is recovered from the device, and the result is communicated to the device. On our side, actually, we are moving everything, almost everything, to be on the right let's say statement. We are keeping one small task that needs to be running on the cloud for one specific reason, is the cold start. Okay, so we are having difficulties to start the models directly on the edge. So we are doing a small task of initializing the model on the cloud, initializing a generic model actually on the cloud, and then sending it to the device, and the rest should be done on the device. All right, I think I still have just 5 minutes, so I will start. I will try to be as fast as I can. All right, so what we are doing, so we have built an application that we have implemented on the watch and the smartphones. We collected around 25 gig of data on different activities. We have used different people. We got around 20 million samples, which correspond to 60 hours of data. For the pre-processing, we have done the classical things, the scaling, the outlier detection, balancing the data, so on and so forth. We have done sort of feature engineering, created some features, and then we had the space of 41 initially that we have increased later to 100, around 160 features. Then we have built the AI model. For this, we have relied on the Siamese networks and the few shots learning to do the prediction, or to build the model directly in that. Why did we use that? Because it's a sort of a very light version of neural networks that can run actually directly on small devices. You do not need a lot of data, for example, to do that, to do the learning. So we tested different versions of that, and we were able to build the models directly on the edge. We have used some post-processing on the results to be able to make sure that things are working fine. There was also some data pre-processing that was injected directly on the thing. So I put this slide actually to discuss a little bit in details the Siamese network and the few shots learning. I hope everybody is familiar with that, but we don't need a lot of data. Basically, you need few examples, few shots learning, few examples of your activities to be able to build your network. So you can build a specialized network for each activity, and then you can use that to predict your stuff. And what we do in our case, we do actually an incremental learning, in the sense that that's why we use the contrastive loss, is that the classes are not known ahead of time. right? We have few classes that we know ahead of time just to initialize the model. We start with 2 in general, but then new classes can come, and to be able to tackle that part, we need actually to have also functions that can sort of support that reasoning. So we have done very generic architecture of neural network, and then we have learned everything. You obtain very good results. That's not the important part, actually. That was just for the test, for checking that the models are working fine. The interesting part actually is to see if when we inject new classes or new activities, things work or do not work, right? So we have done a sort of an initial thing where we removed one activity from the data, and then we have built our model, and then we wanted to predict the new activity that the model doesn't know yet, right? So the performance of the model goes really, really bad, and the missing class is just 20%, right? Then we have done a different thing where we have actually added very few samples. We injected very few samples on the initial model. So we retrained the model. We built the model with 4 classes. Then we retrained the model with the new class. We added the new class, but we have added just 100 samples from the new class, right? And then we recovered, actually, we were able to recover the initial performance of the whole model. And then even the new class actually became known from the model. All right, so at the end of the day, we end up with sort of an software and infrastructure that is small enough. It's around everything. When you combine, when you package everything, you get sort of 5 megabytes of tool of software that could be easily sort of injected in or embarked, I would say, in an edge device that is equivalent actually to 2 high definition pictures that we are taking every day in our mobile phone. There is a very short video from our side. I think the sound doesn't work, unfortunately, but I will try to explain what's going on here. So this is the Magneto, and this is George working with us, who's doing the demonstration. So he's just trying to use in real time the application. Okay, so here you have the walk, for example. He's working, everything is fine, he is still. Now he's trying to predict a new activity that the system doesn't know, right? He's going basically sort of using his arm in a circular way to try to predict, and it's not predicting, right? Of course, like the system doesn't know it. So what he's going to do actually is to create a new activity that he will call gesture, and then the application will ask for some samples, right? We get some samples, so he's collecting now. So collecting and collecting some samples. Okay, now he will start training the new, injecting basically the new activity in the existing model. And this is done again on the phone. Of course, it will not come straight away. You have a phone, just a normal phone that is executing the task. But then at the end, you will get your new model, just trying to go a little bit faster. Yeah, the model has been updated, and the system will ask you to use the new model. So now he will try to see if the new activity has been integrated. Yeah, as you see, the new activity now is integrated. Again, everything that you have seen here has happened directly on the edge. There was no communication with the cloud. The previous classes, they have stayed. The new model, the new class actually has been injected and added to the existing model, and the system is able to predict that new class that was not able to be predicted before. Sorry, I'm trying to exit this slide if I can. Oops. Okay. All right, just 2 slides and I should be done. So we are doing the inference on the edge. We are also doing the learning on the edge. There is some work to do in terms of performance, but the initial objective, I think, is achieved. There is no latency. In terms of inference, there is no latency, and the user data stays totally on the edge. There are issues with the catastrophic forgetting. Basically, when we add more classes, we tend to lose the quality of the previous classes. This is something that we have tackled in a new paper that I have shown you just before. You have new activities learning needs. So what kind of activities that you need to learn, and then how to adapt the data collection that we had before with potential new activities. We cannot be generic from this perspective. Data augmentation, we're trying to investigate also how we could increase the data. We are working on releasing also a data set, a public data set on this kind of activities, and then how to bring this thing to the end user. Just the last slide on the challenges on related not to the Magneto project, but related to the Edge AI or Edge ML in general. There is a lot of work to be done on learning generalization and adaptation. So we learn things that may be too specialized. How do we generalize these kind of things? We have, I think the track to follow would be to combine different paradigms of edge machine learning. Theoretical foundation, most of the work that is done now is sort of on the practical side. There is some theory, but I think there is a room to do a lot of theory there. And this research, I guess, should come from universities. Architecture for heterogeneity and scalability, that's a critical thing if we want this aspect to succeed. In the sense that, as I said in the beginning, you have implementations, but implementations are done on very specific devices that are actually good devices. They have good computation power. So how can we combine different devices to achieve specific goal? Privacy. I think there is a lot of work that is done on privacy. By definition, like the distributed learning is preserving some privacy, but again, there are other risks when you are distributing your data. You need also to secure your device. For example, the devices have to be secured, so it provides actually more access points to hackers and these kind of things. So, for example, data poisoning, for example, could be an issue on this side. Hybrid approaches, I think the solution, honestly, is to will come from the combination of different paradigms. We cannot just solve everything. We cannot solve everything with one model, that's for sure, but we need to work on this combination. Data quality is a huge issue. Devices, they have their own weaknesses when it comes to the quality. The sensors, we cannot control much. So we have to handle this kind of thing. We're launching a specific project on the data quality on the Edge ML. The framework extensions, again, you have few frameworks that are working on specific devices. When you go to another device, to another architecture, you need to have either another framework or do things, a lot of manual work. This has to be tackled. And the last point is the standardization. There are a lot of standardization bodies that are handling or discussing these aspects, but still these things are under discussion. There is no pure recommendation that came to handle specific points on this aspect. I think I am done. Thank you very much for your time. I hope I was not too long. Thank you.